This lecture will provide a brief introduction to radar, LiDAR, and vision systems for automotive safety applications, with a focus on comparing the sensors' technologies. Radar, or radio detection and ranging, and LiDAR, light detection and ranging, are sensor systems that actively send out radio waves and laser light, respectively, measuring the returning reflections. Most vision systems, on the other hand, are passive safety sensors systems that acquire ambient light from the scene to build up an image. Here you see the conceptual comparison of the output from three different sensor types: vision, LiDAR, and radar. To the left, a single-camera vision system passively captures the light from the scene in the two-dimensional matrix of pixels. In the middle, a bird's-eye view of a simple 1B 2D scanning LiDAR is showing the same objects as in the video, the points being individual measurement points on the objects. Finally, to the right, objects are represented as blobs from the radar sensor. All three sensor types can be used as a basis for identification and tracking of objects surrounding the vehicle. These three extra vehicle sensor types each have their respective pros and cons. This table shows an overview of some main features, with plus markings when the sensor type is reasonably good and minus when it's poorer. For example, both LiDAR and radar provide reasonably good estimates of ranges to objects, while vision systems typically provide poorer range estimates. On the other hand, vision and LiDAR sensors are better than radar sensors to determine angles to objects. In addition to range and angle to objects, the estimates of relative velocities to tracked objects are important. As you see, radar sensors provide good estimates of velocity. Actually, radar can measure velocity directly using the Doppler effect, while both vision and LiDAR sensors need to track the object over time and derive the speed over multiple range and angle measurements. The nighttime capabilities are mainly related to active versus passive sensing, where both LiDAR and radar actively sends out laser light and radar pulses, respectively, while most cameras are capturing the light passively without sending out anything. The weather capabilities of vision systems are generally poor. Consider that the degradation in human vision systems is present also for most vision systems. For LiDAR, there are techniques to make the best of bad weather, such as handling multiple reflections through rain or snow, and then choosing the most likely to be a solid object. But using transmitted light clearly has its limitations. Radar typically have much better adverse weather performance than both vision systems and LiDAR. Vision systems have until relatively recently been standing out as the extra-vehicle sensor with the best object classification capabilities. However, as the 3D LiDAR sensor has evolved, the additional information of direct range and angle measurements in 3D have improved high-end LiDAR object classification capabilities a lot. It should also be noted that the combination of vision and LiDAR, or vision and radar systems, are very common in traffic safety and automated vehicle applications. By combining two or more sensor types, their features complement each other, providing redundancy where both sensor types perform well.